Hi everyone and welcome. I'm so glad that you're here. Today we're going to take you from never having flown a rocket to standing safely at a launch pad, finger on the button, knowing exactly what you're doing. This is hosted by Up and Above Space and it's meant for total beginners, so don't worry if you've never touched a rocket before. We're going to cover the fun stuff and the safety stuff in equal measure because the best flights are the safe ones. After the slides, we'll jump into a live OpenRocket demo where we design our rocket together. Let's get into it. Here's our flight plan for today. We'll start with the basics: what model rocketry actually is, why people love it, who can do it, and where you can fly. Then we'll open up a rocket and look at how it all works, including those mysterious motor codes. The biggest chunk is safety, because that's what lets you keep doing this for years. And we'll finish with how to get flying yourself with your very first flight kit. Before we get into the how, let's watch what it all leads to. This is a real flight from our American Rocketry Challenge team lifting off on an F-32 T6 motor. The igniter lights, the motor roars, and the rocket is gone off the pad in a heartbeat. Keep this picture in your head for the rest of the session because everything we cover, the parts, the motor codes, the safety habits, is what makes a clean flight like this one happen. Let's roll it.
2, 1.
Let's start at the very beginning. Section 1, the basics. By the end of this section, you'll know what model rocketry is, why it's such a great hobby, who is allowed to do it, and where you can safely fly. So what is model rocketry? In plain terms, it's building a lightweight rocket out of things like cardboard, balsa wood, and plastic, then flying it on a small pre-made engine you buy in a store. The rocket shoots up, a parachute or streamer pops out near the top of the flight, and it floats gently back down so you can fly it again. The key word is recoverable. These aren't fireworks, and they're not weapons. They are carefully designed flying models with built-in safety used by kids, families, schools, and engineers all over the world. Why do people love this hobby? A few reasons. First, it's real rocket science that you can hold in your hands. You learn about thrust, stability, gravity, and air, and you see it happen instantly. Second, the build is genuinely satisfying. You make something, you paint it, you make it yours. Third, and I can tell you from experience, that moment of launch never gets old. The whoosh, the climb, the parachutes. And finally, it's a community. Clubs, families, and schools fly together. It's science, craft, and a little bit of adrenaline, all at once. Now, you may be asking, who can do model rocketry? Honestly, almost anyone. Beginner kits are recommended for about age 10 and up, and younger kids can absolutely fly with a parent or teacher helping. For the small motors we use as beginners, you do not need a license or special certificate. The main rule is a simple, responsible adult is present and you follow the safety code. As you grow into bigger, more powerful rockets later on, that's when certification and extra rules come in. But to start, you just need curiosity and an adult nearby. Where can you actually fly? You want a big, open, grassy space with no people nearby and nothing that can catch fire. Think large parks, sports fields, or open farmland with permission from the owner. What you want to avoid is just as important. Stay far away from buildings, roads, power lines, trees, and dry brush. Never ever fly anywhere close to an airport. Additionally, it's important to check local rules first because some parks do not allow rocket launches. A good field is flat, open, and clear in every direction. We'll talk about exactly how big it needs to be in a few minutes. On the screen is a bird's eye view of two fields, one ideal and one not ideal. On the left is a good site. One open field with a clear circle of empty space all the way around the launch pad. Nothing for the rocket to hit and plenty of room to drift and still land safely. On the right is a bad site. Same size field, but look what's crowded around it. A row of houses and a road right at the top, tall trees on one side, power lines on the other, and a pond. The safety circle bumps right into all of it. If your circle touches a road, a roof, trees, or wires, that is not your spot. You want the picture on the left. Now, let's open a rocket up. Section 2 is all about how a rocket is built and how it flies. We'll name the parts, see how the motor pushes the rocket up, decode those letters and numbers on the motor, and learn how the rocket comes back down in one piece. At the very top of the rocket is the nose cone, which is pointed to slice through the air. Inside the body tube is the recovery system, usually a parachute plus some flame-resistant wadding that protects it. The motor sits in the motor mount at the bottom. The fins at the back are what keep the rocket flying straight like the feathers on an arrow. And a small launch lug, like a little straw on the side, slides onto the launch rod to guide the rocket as it leaves the pad. These 5 parts, or variations of them, are integral to every rocket. So how does the motor actually work? It happens in 4 quick steps. First, an electric igniter lights the solid propellant. Second, the propellant burns and pushes hot gas out the back, and that thrust shoves the rocket up fast. Third, the propellant runs out and there's a delay charge that makes a smoke trail while the rocket coasts up to its highest point. And fourth, at the top, an ejection charge fires forward and pops the nose cone off to release the parachute. When shopping for your first motor, you may see codes like the one displayed on the screen. Every motor has a code like this one, even the big ones that power actual rockets. Being able to read these codes makes it much easier to pick the correct motor for your application. The letter is the power class. Each letter up the alphabet is roughly double the power of the one before, so a B is about twice an A, and a C is about twice a B. The first number is the average thrust, or how hard it pushes. And the last number after the dash is the delay in seconds, how long it coasts before the parachute pops. So C65 means a C-class motor, 6 newtons of average push, and a 5-second delay. Beginners usually start with A, B, or C motors. How does the rocket get back down safely? That's the job of the recovery system, and there are a few different kinds. The most common one is a parachute, which gives a slow, gentle landing, perfect for bigger or heavier rockets. The next is a streamer. A streamer is a long, bright ribbon that flutters down faster, which is great on windy days, so your rocket doesn't drift into the next county. And some small rockets use tumble recovery, where they just flip end over end and fall slowly because they're so light. Whatever the method, the goal is the same. Bring it down slow enough that nothing breaks. This next section is the most important, so let's slow down. Safety first. None of this is scary, it's just a set of simple habits that keep everyone safe and keep the hobby fun. We're going to cover the safety code, how big your field needs to be, the launch rod, the weather, your pre-flight checklist, the countdown, and how to get your rocket back politely and safely. There's a set of rules called the Model Rocket Safety Code written by the National Association of Rocketry. Clubs all over the world follow it, and so should you. Here are the big ideas. Use only certified store-bought motors, never homemade ones. Always use an electrical launch system with a safety key so nothing fires by accident. Point the launcher within 30 degrees of straight up and never at people. Keep everyone back a safe distance. Make sure the recovery system works before you fly, and only launch in good, clear, calm weather. We're going to walk through several of these in detail now. So how big does the field actually have to be? The bigger the motor, the more room you need, so the rocket has space to come down safely without drifting into trouble. The safety code gives a minimum field size for each motor class. For the small A motors, you need a field at least 100 feet across. A B needs 200, a C needs 400 feet. Step up to a D and you're at 500, and E through G motors need 1,000 feet, which is over 3 football fields. Here's a simple rule. If you're not sure your field is big enough, it isn't. Pick a smaller motor or a bigger field. Here's another exact number to know. How far everyone stands back from the pad once the rocket is ready. Once again, it depends on the size of the motor. For the beginner motors, A through D, everyone stays at least 15 feet away, about 5 meters. Step up to the bigger E, F, and G motors, and that doubles to 30 feet, about 10 meters. When in doubt, stand farther back. Nobody ever got hurt being too far away. Now, let's talk about the launch rod. The launch rod is the thin metal rod that the rocket slides up as it leaves the pad. Its job is to keep the rocket pointed straight until it's moving fast enough for the fins to take over and steer it. If the rod is too short, the rocket leaves it while still moving slowly and can wobble or fly in the wrong direction. For typical beginner rockets on A, B, and C motors, a standard rod about 3 feet or 1 meter long works great. Larger and heavier rockets need a longer rod or launch rail. And always put a little safety cap on top of the rod when you're not flying so it pokes no one in the eye. Weather matters a lot. The big number to remember is 20. Never launch if the wind is stronger than 20 miles per hour. In any wind, rockets do something called weathercocking, where they turn and lean into the wind as they climb. That's normal, but it means a windy day sends your rocket sideways and far away. You also want a clear sky so you can actually see your rocket, and you never launch into or near clouds. And of course, no launching in rain or storms. The best flying days are calm, clear, and bright. If the flags are snapping and the trees are bending, it's a good day to stay home and build instead. Right before you fly, run through this checklist every single time. Even experienced flyers do it. 1. Is the motor pushed in and locked in place? 2. Is the recovery wadding in and is the parachute folded loosely so it opens? 3. Is the nose cone on with a friction fit, snug but not stuck? 4. Are the fins solid and not cracked? 5. Is the igniter pushed all the way up to the propellant and clipped to the launch wires? And finally, is everyone sitting back with the area clear? When all those are yes, and only then, you're ready to put the safety key in. A 30-second checklist prevents almost every bad flight. Now, the fun part. Once the key is in and everyone is back, you call out a loud countdown so everyone knows it's coming. The loud countdown is a safety tool. It tells people to look up and pay attention. But if you press the button and nothing happens, don't worry. That's called a misfire, and here's the golden rule. Do not run up to it. Firstly, remove the safety key so it can't fire. Then, wait at least 60 seconds before you walk up to the rocket. Most misfires are just a bad igniter. Stay calm, wait, swap the igniter, and try again. And what if your chute doesn't open? Here is a real one from our own field. This rocket flew beautifully off the pad, but the parachute never opened, so it came straight back down and buried its nose in the grass. Rocketeers call that a lawn dart, or a ballistic recovery. It usually comes down to a few things. The parachute was packed too tight or got scorched because the wadding was missing, or the motor's delay was wrong for the flight, so the ejection charge fired at the wrong moment. The good news is that no one was near it because we followed safety procedures and picked a correctly sized field. This is exactly why we run the pre-flight checklist and simulate the delay first. Respect the recovery system and your rocket comes home in one piece. After the flight, you go get your rocket. This is recovery and retrieval etiquette, basically good manners on the field. It is important to watch your rocket all the way down so you know where it lands. Wait until it's fully on the ground before you go and walk. Don't run, especially near other people's pads. Never chase a rocket across a road or onto someone else's property without asking. If it lands somewhere tricky, like a tree, just leave it rather than doing something risky. And give a heads up to others if a rocket is drifting their way. Be the kind of flyer other people are happy to share the field with. Alright, last section, and this is where you take the next step. Let's talk about the very first kit you should buy, a few words you'll hear around the field, and what comes right after this webinar. What should you actually buy first? The easiest path is a beginner set, which usually comes with a ready-to-fly or easy-to-build rocket, plus the launch pad and the controller. These kits usually include everything you'll need, but sometimes they don't, so it's important to check. If the kit doesn't include it, you'll need to buy a pack of motors, and A through C is perfect. Additionally, you'll want some recovery wadding to protect your parachute. Look for the words ready to fly or easy to assemble on the box. That gets you everything you need to launch on day one without a workshop full of tools. Here's a quick glossary so the words you'll hear on the field make sense. Apogee is the highest point of the flight, where the parachute pops. Thrust is the push from the motor. The ejection charge is the little blast that deploys the recovery system. Weathercocking, as previously stated, is turning into the wind. Wadding is the flame-resistant padding that protects your chute. An impulse is the total power of the motor, the things those letters measure. Don't worry about memorizing all of these now, as they'll become second nature after a flight or two. Before we jump into the demo, let me tell you what OpenRocket actually is. It's a free, open source program you can download on any computer. You build your rocket on screen, part by part: the nose cone, the body, the fins, the motors, and the software knows the physics. The best part is that you can test the rocket safely before you spend a penny or cut anything. It's like a flight simulator for the rocket you want to build. So why bother before building? As I just said, OpenRocket answers the big questions for you. It shows your rocket in 3D as you design it. It checks stability so you know it will fly straight up instead of spinning out. It lets you try different motors without buying a single one. And it runs a full flight simulation that predicts how high you'll go, how fast, and exactly when the parachute should come out. That's the delay number we talked about earlier. In the demo, you'll watch all 4 of these happen live. Now we're going to switch over to OpenRocket. We're going to build a rocket together on screen, change the fins in the nose cone, pick a motor, and then watch the software predict exactly how high it goes and how it comes down, all before we ever build a real one. I'll see you in the demo. So this is OpenRocket. On the top right, you can see the parts panel where we can select parts to insert into the build area, which is down here. In the top left, you can see a diagram of our rocket, which we'll fill up later. In the bottom left, we have all of our data, like our apogee, max velocity, and max acceleration. And in the middle right, we have the stability, which is going to be really important. And you want this to be around 1.5 calibers to 2.5 calibers. And OpenRocket will, of course, do all of the calculations. So you just need that number to be between 1.5 and 2.5. So what we're going to do is start with the nose cone. As you can see, there are a ton of options here if you bought a nose cone, but we're just going to assume that this one is 3D printed. So we're going to use Hack Series, which tends to be best in my testing. We're going to change the base diameter to 3 centimeters, as that's around the size of a beginner rocket that you will be launching. And we're going to change the material to PLA, which is the type of plastic that most 3D printers use. And the finish, it's going to be unfinished. This is just no sanding, no painting, so it's like really easy to get started and get into it. Next, we're going to go on to the body tube. As you can see, there are a ton of options, and all of them have an outer diameter the same as that of the nose cone. But for now, we're just going to go for a cardboard one, and we're going to change the length to 25 centimeters. Also, the wall thickness should be around 1 millimeter, not 2 millimeters, so we're going to change that. And again, change it to unfinished. Next, we have the fins. They're trapezoidal, elliptical, freeform, and tube fins. Tube fins tend to be good, but they're really heavy. Elliptical tend to be good, but they're really fragile. And trapezoidal tend to be in between, where they're good, but they're not hard to get right, like elliptical and tube fins are. And then freeform, you just make your own. So today we're just going to go with elliptical. We're going to use 3 fins. And you can see the stability number is really high right now, but that's because we haven't added any mass yet. So we're going to lower the height to 3 centimeters and the root cord to 3 centimeters as well. See, that makes it smaller and also brings down the stability, which is what we want, because we want it, again, to be between 1.5 and 2.5. So now we're going to add an engine block. Again, there are a ton of options here. Since we're using an A, B, or C motor, we want an inner diameter of around 1.8 centimeters. And the length depends on your motor, but I'm just going to change it to around 8 right now, as that should fit all of them. And then this will again be made out of PLA, as that's what I usually use, but of course when you're building you can use whatever materials you have on hand, or just if you're inputting it to simulate, just use the materials that your rocket used that you bought. Next, we're going to add a parachute, which is, of course, really important for recovery. For a rocket this small, you could also use a streamer, but I always like to go with a parachute as it's the most controlled. Again, there are a ton of choices here. We're going to use a 30 centimeter parachute, which is a little big, so we're actually going to change it to around 15 centimeters. And then we're going to move it down a bit just so that it's in the right position when when everything will be on, like the nose cone. Next, we're going to add a mass component, and this is just the represents the recovery wadding, which is of course really important so your parachute does not burn. And we're just going to move it down to right near where the motor is. This is around 5 grams. As you can see, our stability is around 1.28, but we still have not added motors yet, so that will change. Next, we're going to add a launch lug or a rail button. For smaller rockets like this, you should use a launch lug. And of course, there are a ton of options again. And right now we don't have a motor, so we can't really launch. But before that, we need a coupler for the nose cone so it can actually connect the body tube. So we're going to go to tube coupler, close this, change the outer diameter to around 3 centimeters. We'll move it down so it's just connected at the bottom. Then lower the length. And now the nose cone will be connected to the rocket. So we're going to now go into motors and configuration. We're going to select body tube as the motor mount, create a new configuration. For this rocket, we're going to use a C6 motor and there are a ton of ejection charge delays to pick from, which is basically how long before the ejection charge goes off after the motor is done burning out. We're just going to keep it at 0 for now. And so as you can see, the stability dropped to 0.568, which is really not good. It would indicate a lot of tumbling. So we're going to go back into the fins, and we can either add another fin, which doesn't help enough, or we can increase the height, which will help a lot more. And then you have to increase the root cord. So this is at around 1.65 calibers, which is good for a rocket. And will mean that it's not tumbling, but there's also not too much weathercocking, meaning it won't turn into the wind. Next, we're going to go into the flight simulations tab. So what we're going to do is you can see that this is already simulated, so you can see the velocity off the rod, you can see the apogee, the velocity at deployment of the parachute, the optimal delay for the motor. So if we wanted to, we could go back and change the delay and buy a different motor with a more optimal delay so that the rocket goes higher. And you can also see the ground hit velocity, which is a bit high, so you might want to make the parachute bigger. But for now, since this is just a demonstration, I'll keep it as is. Next, we can plot and export. And what we can do is press plot, and then you can see the actual flight path of the rocket, including the altitude, the velocity, and everything in between, including like the acceleration when it hits the ground, like basically the entire path of the rocket. What's important to note is that this is not perfectly accurate, and you should always take these results with a grain of salt. You can also change things like wind speed and so your launch is more your simulation is more accurate when compared to your launch. You can change the launch rod length, the latitude, longitude, altitude, pretty much everything, and it lets you do everything really well. And so like you can change anything on this rocket, and you can immediately see how it affect the apogee And yeah, that's like OpenRocket allows you to test a lot of different things, and it allows you to test your rockets before you launch, which is really good, and it helps you actually build new rockets if you want to build your own rockets. So this is the OpenRocket demo. Let's go back to the video. Thank you so much for spending this time with us. You now know what model rocketry is, how a rocket works, and most importantly, how to fly it safely. Build carefully, check your work, respect the weather, and always keep an adult close. Do that, and you're going to have an amazing time. From all of us at Up and Above Space, welcome to the hobby. Now let's go fly.